A flow battery, or redox flow battery, is a type of rechargeable battery where rechargeability is provided by two chemical components dissolved in liquids contained within the system separated by a membrane. Ion exchange occurs through the membrane while both liquids circulate in their own respective space. Cell voltage is chemically determined by the Nernst equation and ranges, in practical applications, from 1.0 to 2.2 volts. A flow battery is technically akin both to a fuel cell and an electrochemical accumulator cell. While it has technical advantages such as potentially separable liquid tanks and near unlimited longevity over most conventional rechargeables, current implementations are comparatively less powerful and require more sophisticated electronics. The energy capacity is a function of the electrolyte volume and the power to the surface area of the electrodes. Construction principle. A flow battery is a rechargeable fuel cell in which an electrolyte containing one or more dissolved electroactive elements flow through an electrochemical cell that reversibly converts chemical energy directly to electricity. Additional electrolyte is stored externally, generally in tanks, and is usually pumped through the cell of the reactor. Although gravity feed systems are also known, flow batteries can be rapidly recharged by replacing the electrolyte liquid while simultaneously recovering the spent material for re-energization. In other words, a flow battery is just like an electrochemical cell, with the exception that the ionic solution is not stored in the cell around the electrodes. Rather, the ionic solution is stored outside of the cell, and can be fed into the cell in order to generate electricity. The total amount of electricity that can be generated depends on the size of the storage tanks. Types. Different classes of flow cells have been developed, including redox, hybrid and membraneless. The fundamental difference between conventional batteries and flow cells is that energy is stored not as the electrode material in conventional batteries but as the electrolyte in flow cells. Redox. The redox cell is a reversible cell in which electrochemical components are dissolved in the electrolyte. Redox flow batteries are rechargeable. Because they employ heterogeneous electron transfer rather than solid-state diffusion or intercalation, they are more appropriately called fuel cells than batteries. In industrial practice, fuel cells are usually, and unnecessarily, considered to be primary cells, such as the H2O2 system. The unitized regenerative fuel cell on NASA's Helios prototype is another reversible fuel cell. The European Patent Organization classifies redox flow cells as a subclass of regenerative fuel cells. Examples of redox flow batteries are the Vanadium Redox Flow Battery, Polysulfide Bromide Battery, and Uranium Redox Flow Battery. Redox fuel cells are less common commercially, although many systems have been proposed. Researchers announced a prototype, zinc polyiodide flow battery with an energy density of 167 Wh/L. Older zinc bromide cells reach 70 Wh/L. For comparison, lithium iron phosphate batteries that store 233 Wh/L. The zinc polyiodide battery is claimed to be safer than other flow batteries given its absence of acidic electrolytes. Non-flammability and operating range of -4 to 122 degrees Fahrenheit that does not require extensive cooling circuitry, which would add weight and occupy space. One unresolved issue is zinc buildup on the negative electrode that permeated the membrane, reducing efficiency. Adding alcohol to the electrolyte contained the problem. When the battery is fully discharged, both tanks hold the same electrolyte solution, a mixture of positively charged zinc ions and negatively charged iodide ion, I. When charged, one tank holds another negative ion, polyiodized I3. The battery produces power by pumping liquid from external tanks into the battery's stack area where the liquids are mixed. Inside the stack, zinc ions pass through a selective membrane and change into metallic zinc on the stack's negative side. Traditional flow battery chemistries have both low specific energy and low specific power. However, recently a high aerial power of 1.4 W per square centimeter was demonstrated for hydrogen-bromine flow batteries, and a specific energy was shown for hydrogen-bromate flow batteries. In 2015, a system was demonstrated using organic polymers and a saline solution with a cellulose membrane. The prototype withstood 10.000 charging cycles while retaining substantial capacity. The energy density was 10 watt-hours. L. Current density reached 100 mA per square centimeter. Hybrid. The hybrid flow battery uses one or more electroactive components deposited as a solid layer. In this case, the electrochemical cell contains one battery electrode and one fuel cell electrode. This type is limited in energy by the surface area of the electrode. Hybrid flow batteries include the zinc-bromine, zinc-cerium and lead-acid flow batteries. Membraneless. This battery employs a phenomenon called laminar flow in which two liquids are pumped through a channel. They undergo electrochemical reactions to store or release energy. The solutions stream through in parallel, with little mixing. The flow naturally separates the liquids, eliminating the need for a membrane. Membranes are often the most costly component and the most unreliable components of batteries, as they can corrode with repeated exposure to certain reactants. The absence of a membrane enabled the use of a liquid bromine solution and hydrogen. This combination is problematic when membranes are used, because they form hydrobromous acid that can destroy the membrane. Both materials are available at low cost. The design uses a small channel between two electrodes. Liquid bromine flows through the channel over a graphite cathode and hydrobromous acid flows under a porous anode. At the same time, hydrogen gas flows across the anode. The chemical reaction can be reversed to recharge the battery, a first for any membraneless design. One such membraneless flow battery published in August 2013 produced a maximum power density of 7,950 W per square meter, 3 times as much power as other membraneless systems, and an order of magnitude higher than lithium-ion batteries. Organic. In 2013, researchers announced the use of 9,10-ANTHRAQUINONE2, 7-disulfonic acid, a quinone, as a charge carrier in metal-free flow batteries. Each of the carbon-based molecules holds 2 units of electrical charge, compared with 1 unit in conventional batteries, implying that a battery could store twice as much energy in a given volume. AQDS undergoes rapid, reversible 2-electron, 2-proton reduction on a glassy carbon electrode in sulfuric acid. An aqueous flow battery with inexpensive carbon electrodes, combining the quinone, hydroquinone couple with the Br2, Br- redox couple, yields a peak galvanic power density exceeding 6,000 W per square meter at 13,008 per square meter. Cycling showed greater than 99% storage capacity retention per cycle. Volumetric energy density was over 50 watt-hours, L, and specific energy density over 50 watt-hours per kilogram. The organic anthraquinone species can be synthesized from inexpensive commodity chemicals. This organic approach permits tuning of the reduction potential and solubility by adding functional groups. Adding 2 hydroxy groups to AQDS increases the open circuit potential of the cell by 11%. In 2014, another example used ANTHRAQUINONE2 sulfonic acid or ANTHRAQUINONE2, 6-disulfonic acid on the negative side and 1,2-dihydrobenzoquinone, 3,5-disulfonic acid on the positive side. The battery was claimed to last for 5,000 cycles without degradation. In 2015, researchers improved the chemistry and replaced the hydrobromous acid used as an electrolyte with a far less toxic alkaline solution, an ferrocyanide. The higher pH is less corrosive, allowing the use of inexpensive polymer tanks. The increased electrical resistance in the membrane was compensated by increasing the voltage. The cell voltage was 1.2. The cell's efficiency exceeded 99%, while round-trip efficiency measured 84%. The battery has an expected lifetime of at least 1,900 cycles. Energy density was 19 watt-hours per liter. Another 2015 project employed methyl vilogen as analyte 4-hydroxy-2,6,6-TETHYLPIPERIDIN-1 oxal as catholyte, plus sodium chloride to enable discharging. The water-based liquid electrolytes were designed as a drop-in replacement for current systems without replacing existing infrastructure. A 600 mW test battery was stable for 100 cycles with nearly 100% efficiency at current densities ranging from 20 to 100 mA per square centimeter, with optimal performance rated at 40 to 50 mA, at which about 70% of the battery's original voltage was retained. Methyl hydride proton flow batteries integrate a metal hydride storage electrode into a reversible proton exchange membrane fuel cell. During charging, PFB combines hydrogen ions produced from splitting water with electrons and metal particles in one electrode of a fuel cell. The energy is stored in the form of solid-state metal hydride. Discharge produces electricity in water when the process is reversed and the protons are combined with ambient oxygen. Metals less expensive than lithium can be used and provide greater energy density than lithium cells. Nano Network. In 2014, a technology was announced that uses lithium-sulfur chemistry arranged in a network of nanoparticles. The network eliminates the requirement that charge moves in and out of particles that are in direct contact with a conducting plate. Instead, the nanoparticle network allows electricity to flow throughout the liquid. This allows more energy to be extracted. In August 2014, the Quanti Sport limousine was approved for testing on public roads using the NanoFlow registered sign system with a claimed energy or power density of 600 watt-hours per kilogram. Semi-solid in a semi-solid flow cell. The positive and negative electrodes are composed of particles suspended in a carrier liquid. The positive and negative suspensions are stored in separate tanks and pumped through separate pipes into a stack of adjacent reaction chambers, where they are separated by a barrier such as a thin, porous membrane. The approach combines the basic structure of aqueous flow batteries, which use electrode material dissolved in a liquid electrolyte, with the chemistry of lithium-ion batteries. Dissolving a material changes its chemical behavior significantly. However, suspending bits of solid material preserves the solid's characteristics. The result is a viscous suspension that flows like molasses. Polymer. A novel flow battery concept that is based on redox-active, organic polymers and dialysis membranes was announced in 2015. The polymer-based redox flow battery uses functionalized macromolecules being dissolved in water as active material for the anode as well as the cathode. Thereby, metals and strongly corrosive electrolytes, like vanadium salts and sulfuric acid, are avoided and simple dialysis membranes can be employed. The membrane, which separates the cathode and the anode of the flow cell, works like a strainer and is produced much more easily and at lower cost than conventional ion-selective membranes. It retains the big, spaghetti-like polymer molecules, while allowing the small counterions to pass. Chemistries. There are a wide range of chemistries that have been tried for flow batteries. Advantages and disadvantages. Redox flow batteries, and to a lesser extent hybrid flow batteries, have the advantages of flexible layout, long cycle life, quick response times, no need for equalization, charging and no harmful emissions. Some types also offer easy state of charge determination, low maintenance and tolerance to overcharge, over-discharge. On the negative side, flow batteries are rather complicated in comparison with standard batteries, as they may require pumps, sensors, control units and secondary containment vessels. The energy densities vary considerably but are, in general, rather low compared to portable batteries, such as the Li-ion applications. Flow batteries are normally considered for relatively large stationary applications. These are for load balancing, where the battery is connected to an electrical grid to store excess electrical power during off-peak hours and release electrical power during peak demand periods. The common problem limiting the use of most flow battery chemistries in this application is their low aerial power, which translates into a high cost of power. Storing energy from renewable sources such as wind or solar for discharge during periods of peak demand, peak shaving, where spikes of demand are met by the battery. UPS, where the battery is used if the main power fails to provide an uninterrupted supply. Power conversion, because all cells share the same electrolyte per second. Therefore, the electrolyte per second may be charged using a given number of cells and discharged with a different number. Because the voltage of the battery is proportional to the number of cells used, the battery can therefore act as a very powerful DC-DC converter. In addition, if the number of cells is continuously changed, power conversion can also be AC, DC, AC, AC, or DC-AC, with the frequency limited by that of the switching gear. Electric vehicles, because flow batteries can be rapidly recharged by replacing the electrolyte. They can be used for applications where the vehicle needs to take on energy as fast as a combustion-engined vehicle. A common problem found with most RFB chemistries in the EV applications is their low energy density, which translated into a short driving range. Flow batteries based on highly soluble halates are a notable exception. Standalone power system. An example of this is the telecom industry for use in cell phone base stations where there is no grid power available. The battery can be used alongside solar or wind power sources to compensate for their fluctuating power levels and alongside a generator to make the most efficient use of it to save fuel. Currently, flow batteries are being used in solar microgrid applications throughout the Caribbean. But as the electrolyte in flow cells, redox, the redox cell is a reversible cell in which electrochemical components are dissolved in the electrolyte. Redox flow batteries are rechargeable. Because they employ heterogeneous electron transfer rather than solid-state diffusion or intercalation, they are more appropriately called fuel cells than batteries. In industrial practice, fuel cells are usually, and unnecessarily, considered to be primary cells, such as the H2O2 system. The unitized regenerative chemical accumulator cell, while it has technical advantages such as potentially separable liquid tanks and near unlimited longevity over most conventional rechargeables, current implementations are comparatively less powerful and require more sophisticated electronics. The energy capacity is a function of the electrolyte volume and the power to the surface area of the electrodes. Construction principle. A flow battery is a rechargeable fuel cell in which an electrolyte containing one or more dissolved electroactive elements flow through an electrochemical cell that reversibly converts chemical energy directly to electricity. Additional electrolyte is stored externally, generally in tanks, and is usually pumped through the cell of the reactor. Although gravity feed systems are also known, flow batteries can be rapidly recharged by replacing the electrolyte liquid while simultaneously recovering the spent material for re-energization. In other words, a flow battery is just like an electrochemical cell, with the exception that the ionic solution is not stored in the cell around the electrodes. Rather, the ionic solution is stored outside of the cell, and can be fed into the cell in order to generate electricity. The total amount of electricity that can be generated depends on the size of the storage tanks. Types. Different classes of flow cells have been developed, including redox, hybrid and membraneless. The fundamental difference between conventional batteries and flow cells is that energy is stored not as the electrode material in conventional batteries, but a flow battery, or redox flow battery, is a type of rechargeable battery where rechargeability is provided by two chemical components dissolved in liquids contained within the system separated by a membrane. Ion exchange occurs through the membrane while both liquids circulate in their own respective space. Cell voltage is chemically determined by the Nernst equation and ranges, in practical applications, from 1.0 to 2.2 volts. A flow battery is technically akin both to a fuel cell and an electrode.